Hello everyone, welcome to this lesson. In this lesson, I'm going to be introducing you to the central limit theorem, which is one of the most powerful theorems in statistics. We're going to be applying this theorem throughout this quarter as we move forward. Your goals for this lesson is to be able to determine if the central limit theorem can be applied to establish that a sampling distribution is normal, and to be able to compute probabilities using a normal distribution of sample means. I will be explaining what a sampling distribution is, what the central limit theorem is, and what needs to happen or what conditions need to be met for you to be able to use the central limit theorem. Let's go ahead and start by talking about the central limit theorem. As I mentioned before, the central limit theorem is one of the most powerful and useful ideas in statistics. Here we're going to assume that x is a random variable with a distribution that might be known or unknown. It can be any distribution. The central limit theorem says that if we collect samples of size n for the random variable x, then we calculate the sample means and we create a histogram with this sample means. Then the resulting histogram will tend to approximate a normal distribution. So here's a visual to help you out. Let's say that the distributions we have here above are the x distribution. This is going to be the collection of all the observations from the population. Again, this distribution might be a left skewed, right skewed, uniform distribution. It can be any distribution. What we're saying here, if you go ahead and collect samples of size n and you find the mean for each of these samples and you go ahead and construct a histogram, the central limit theorem says that that distribution full of sample means is going to follow a normal distribution. Okay? Now, the central limit theorem has some conditions for us to be able to establish this claim that the sample mean follows a normal distribution. We're going to talk about those conditions below, but here I just want to help you picture the idea. Let's go ahead and say that we're collecting samples of size 40. I can go ahead and collect data for a variable of, let's say, just 40 students. Okay, that is my sample. I go ahead and collect the data for a specific variable that we're measuring, and I come back and I give you the sample mean for those 40 students. Okay? This is a little X bar. Now, let's say you go out there and you randomly select 40 students. You collect data for the specific variable that we're looking at, and you come back and you bring the sample mean. This is a little X bar. This is the mean of your sample. And now let's go ahead and think about having other people do the same thing. Somebody goes, collects data for 40 students, and they bring back X bar. All those little X bars that we're collecting are going to form a histogram. So think about a histogram that was found by collecting little X coming from samples of size 40 in this case. That's our example here. This distribution is known as the sampling distribution. The central limit theorem says that if you go ahead and collect different sample means and you create this histogram, you're going to notice that that histogram follows a normal distribution, regardless of the distribution that the X distribution followed. Now, let's go ahead and talk about the conditions for the central limit theorem. The size n for each sample is required to be large enough. The size of those samples are required to be large enough. And this is going to depend on the original population from which the samples are selected. Now, the rule of thumb is that the sample mean should be at least 30 or more. Or we need to know whether the data came from a normal distribution. The idea here is that as n increases to infinity, as the sample size increases to infinity, we're going to start seeing a normal distribution. Here, the bigger the sample size, the better. I'm just going to go ahead and illustrate this here. I'm going to say if n goes to infinity, we're going to see a normal distribution. Now, here in practice, we need to select a sample size. The rule of thumb is that if your sample size is 30 or bigger, then we can conclude that the sampling distribution is going to follow a normal distribution. Now here, the second sentence says, or the data should come from a normal distribution. What we're saying here is that if we know that X follows a normal distribution, then even if the sample size is less than 30, we can still apply the central limit theorem. If X follows a normal distribution, then the sampling distribution will follow a normal distribution even if the sample size is less than 30. Now, I want to formalize the theorem a little bit more and introduce you to the notation that we're going to be using to refer to the sampling distribution. If you draw samples of size n from a random variable distribution, then as n increases, that is, as n increases to infinity, the random variable x bar, which consists of sample means, tends to be normal. And to be more specific, we would say normal distributed. Now, the sample size needs to be at least 30. That means n has to be greater or equal to 30. If it helps, go ahead and write it in words. You can say the sample size has to be 30 or more. If the sample is equal to 30 or more, then the central limit theorem holds. Now, if the random variable x follows a normal distribution, then the central limit theorem holds true even for samples smaller than 30. So earlier I said, if we're considering a random variable x, it might be the case that we know how the distribution looks like. It might be the case that we don't know how the distribution looks like. Now, if we know that the variable x follows a normal distribution, then we can go ahead and apply the central limit theorem. We don't care about the size of the samples. We know that the x bar distribution is going to follow a normal distribution. The distribution of x bar, which is composed of sample means, is what we call the sampling distribution. Now, let me show you the notation that we use. If we're referring to the x bar distribution and we know that it follows a normal distribution, then we're going to use the notation here. X bar follows a normal distribution where the mean of the distribution is the mean of x, and the standard deviation of this distribution is the standard deviation of x divided by the square root of n. So that is the notation that we have here. Again, note that x bar and x have the same mean. So if you know the mean of x, then you know the mean of x. Now, it's not going to be the same for the standard deviation. The standard deviation of x bar, which is denoted as sigma of x bar, this is going to be equal to sigma of x. That is the standard deviation of x divided by the square root of n. If we wanted to calculate z-score, we would take one of the observations coming from the x bar distribution. That would be a little x bar. Then we would say, go ahead and subtract by the mean and divide it by the standard deviation of the distribution. Again, here the standard deviation of the distribution x bar is sigma of x divided by the square root of n. Let's go ahead and look at an example. A unknown distribution has a mean of 90 and a standard deviation of 15. Samples of size n equal to 25 are randomly selected from the population. Here, our x distribution is unknown. We don't know if this distribution follows a normal distribution, a uniform distribution, if it's skewed. We don't know how this distribution looks like. We are being told that the mean of this distribution, and instead of just writing mu, I'm going to write mu of x. That way we know that this is the mean for this unknown distribution. So that mean is equal to 90. The standard deviation here is 15. Instead of just using sigma as we always do, I'm going to write sigma of x again so that we remember that this is the standard deviation of this unknown distribution. This is 15. Now we're being told that samples of size n equal to 25 are going to be taken. They're going to be taken from the population. Now, the central limit theorem says that if x follows a normal distribution, we can apply the central limit theorem. Or if the sample size is 30 or greater, we can apply the central limit theorem. Here, we would not be able to apply the central limit theorem. Why? Because we don't have a normal distribution for x, and the sample size is less than 30. Again, let me make this remark. We don't have a normal distribution for x, and the size of the sample is less than 30. We cannot apply the central limit theorem. If we wanted to apply the central limit theorem, let's say we wanted to apply the central limit theorem, before we use the central limit theorem to claim that the sampling distribution, which is the distribution of x bar, before we can say that this distribution follows a normal distribution, what must we assume about the unknown distribution? What do we have to assume about x? We need to assume that x follows a normal distribution. Again, the sample size is less than 30. Thus, the only way we can apply the central limit theorem is if we assume that x follows a normal distribution. Now, if the sample size was 30 or bigger, then we wouldn't have to make this assumption. We would say the samples are big enough, we can apply the central limit theorem. So again, we're making this assumption. We're saying let's assume that X follows a normal distribution. That way we can apply the central limit theorem. And if we apply the central limit theorem, then now we can say that X bar follows a normal distribution. And now we have to go ahead and state the mean and the standard deviation. The mean is going to be mu of X. The standard deviation is going to be sigma of X divided by the square root of N. So let's go ahead and replace those values. Mu of X is 90. Now sigma of X is 15 and N here is 25. Go ahead and simplify the value of the standard deviation of X bar. What is 15 divided by the square root of 25? The square root of 25 is 5, so 15 divided by 5 is 3. So let me go ahead and replace this expression with 3. Here we have it. The sampling distribution, X bar, follows a normal distribution. The mean of this distribution is 90, and the standard deviation of this distribution is 3. If you're finding the standard deviation of the X bar distribution, you're always going to take sigma of X divided by the square root of N. That is how we found. Now, what does the sampling distribution of means look like? Well, we know that X bar follows a normal distribution. We know that the mean is 90 and the standard deviation is 3. We can go ahead and draw this distribution. Should be a normal curve. The center of this distribution is 90, and we can go ahead and label some standard deviations to the right and left. We have 90 plus 3, which is 93, 96, and 99. Here on the left, we have 87, 84, and 81. So this is a good visual of what the sampling distribution looks like. I'm going to go the extra mile, and I'm going to draw these little X bars came from looking at samples of size 25. Again, imagine I take a sample of 25 members or individuals of the population and I go ahead and calculate the sample. And then you go ahead and do the same thing. You take a sample of 25 individuals from the population and you calculate the mean. And you have other people do the same thing. Or you go ahead and repeat this multiple times. As the repetitions of this goes to infinity, we're going to start seeing this normal distribution. Now that we have established that X bar follows a normal distribution, we can go ahead and find probabilities using this normal distribution. We can answer questions like, find the probability that a sample mean is below 85. Here, let's go ahead and use probability notation. We're being asked, what is the probability of a X bar being below 85? In other words, what is the probability that you go and select 25 individuals from the population and compute the sample mean? What is the probability of that sample mean being less than 85? That is the question we have here. We can answer this question using a calculator, Google Sheets, or Excel. If you're using a calculator, you're going to use normal CDF. And before I type it here, let's go ahead and visualize the probability that we're trying to find. Again, this is the X bar distribution. We're being asked to find the probability. At the center, we have 90. I like to label the center so that I can get a better visual of the area I'm trying to find. So notice, we want to find the area below 85. Let's just say 85 is around here on the left side of the mean. We're trying to find the area below 85. So we're using our calculator. The lower bound is going to be -1 E99, and the upper bound is going to be 85. The mean here is the mean of the X bar distribution, which is 90. The standard deviation is the standard deviation of the X bar distribution, which is 3. So here is the common mistake that I see. Instead of students using 3, I see students using 15. The reason why we're not using 15 here is because we're talking about the probability of X bar being less than 85. If we were talking about the probability of X being less than 85, then yes, we would use 15. But here we're talking about a sample mean. We're not just talking about an observation from the X bar distribution. So again, if you're using a calculator, you're going to use normal CDF. The lower bound is -1 E99. The upper bound is 85. The mean is 90 and the standard deviation is 3. If you're using Google Sheets or Excel, you're going to use norm.dist This function is going to give you the area below the x bar you're considering. Here we want to find the area below x bar equal to 85. So here our observation is 85. Then we need to enter the mean and the standard deviation of this distribution. And then we go ahead and type in true. Go ahead and try this on your calculator or on Google Sheets. You should be getting 0.0478 if you round to 4 decimal places. We can also express this as a percentage. This is equivalent to 4.78%. So the probability of you taking a sample of 25 individuals from the population and finding the mean, the probability of that mean being below 85 is 4.78%. I want you to go ahead and practice this on your own. We're going to set up number 2 together, and then I'm going to ask you to answer the questions below. Here we're going to be looking at a real-life scenario. Cans of cola beverage claims to contain 16 ounces. All cans are filled so that the mean is equal to 16 ounces as labeled, and the standard deviation is equal to 0.143 ounces. Now, we're going to be taking samples of size n equal to 34. They're going to be randomly selected, and the amount of cola is going to be measured. I want you to try this on your own, but I want to take the time to summarize what is being given to us. Okay? So here, X is the distribution of the amount of cola in individual cans. We're given the mean and the standard deviation for this distribution. Let's go ahead and be more specific. We're going to say mu equal to 16. This mu is the mean of X. So let's go ahead and write mu of X equal to 60. We're going to do the same with the standard deviation. 0.143 is the standard deviation of X. We're also being told that the sample size is equal to 34. So n is equal to 34. Here, the sample size is greater than 30. Thus, we can apply the central limit theorem to conclude that the X bar distribution follows a normal distribution. And that is all I'm going to say for this part. Now, you're going to be answering the following question. Find the probability that a sample of 34 cans will have an average amount greater than 16.01 ounces. What are we being asked to find? Let's go ahead and use probability notation. We are finding the probability of a X bar. How do I know I'm talking about an X bar? Because it says, what is the probability that a sample of 34 cans has an average greater than 16.01? They're asking us, what if you go and randomly select 34 cans and you calculate the average, you calculate the mean? What is the probability of that mean being greater than 16.01? So here again, we're asking ourselves, what is the probability of X bar being greater than 16.01? Because we're looking for a probability of a sample mean, we need to use the X bar distribution. We're not going to be using the X distribution. We're going to be using the X bar distribution. Go ahead and answer this question on your own. I'm going to make sure to provide a solution below this video.